Hi guys, in this video we discuss few topics that are necessary for the theorems that follows. Our first topic is principal idol. An idol n of R such that n is generated by some element of R is called principal idol. So the idols 2z, 3z, etc. are principal idols of Z. And likewise, the idol generated by the polynomial x, the idol generated by the polynomial x square plus 1 are principal idol of ring Zx. Next we have a theorem. It states if f is a field, then every idol in fx is principal. We have proof here. Let n be an idol of fx. Then if n equals to 0, then n is principal because n is generated by 0 itself. So suppose n is not equals to 0 idol, then let gx not equals to 0 of n be of minimum degree in n. Then if degree of gx equals to 0, then gx is constant in f. So since f is a field, gx is a unit in f, and since n is an idol containing unit gx, by a theorem n must be equal to the ring fx itself, which is generated by 1. 1 is unit here, so n is generated by 1 and n is principal idol. And if degree of gx is greater than 0, then for a polynomial fx in n, there exist polynomials px and rx such that fx equals to gx times px plus rx by division algorithm. Now rx equals to fx minus gx px, which belongs to the idol n, but we have the degree of rx is less than of degree of gx, but we have gx is of minimum degree in n, so we must have the polynomial rx equals to 0. This polynomial rx equals to 0, and this gives us fx equals to gx times rx. The polynomial fx is generated by gx, so we must have the idol n is generated by the polynomial gx, so the idol n is principal. The theorem is proved. Second theorem we have is the idol generated by polynomial px not equals to 0 idol of fx is maximal if and only if the polynomial px is irreducible over f. Now we proceed to the proof. For the first part of the proof, the idol generated by px not equals to 0 idol of fx is maximal is given to us. To prove is the polynomial px is irreducible over f. Now we have the idol px is not equals to fx because the idol px is maximal. Then by a theorem, the polynomial px does not belong to field f, so the polynomial px is not a constant. Then let the polynomial px equals to rx sx, that is reducible if possible. Then since the idol px is maximal, it is prime also. Then the product rx sx, it belongs to the idol px, implies either rx belongs to the idol px or sx belongs to idol px. But we have the degree of polynomial rx and sx is less than the degree of the polynomial px. Take an example here. This polynomial, when it is reduced, they have degree less than this polynomial. But we have the polynomial px is of minimum degree in the idol generated by px, so there cannot exist such polynomial rx and sx, so the polynomial px is not reducible. Now the second part of the proof, the polynomial px is irreducible over f, is given to us. To prove is the idol generated by px is maximal in fx. Now let n be an idol of fx such that the idol generated by px is proper subset of n and n is proper subset of fx. That means n isn't maximal idol in fx, if possible. Suppose. Then second we have, since f is a field and n is an idol of fx, by our previous theorem, n is principal, so we must have n equals to generated by gx for some gx in fx. The idol px is subset of n implies the polynomial px belongs to idol n. So px must be generated by the polynomial gx. So we must have px equals to gx rx for some rx in fx. This shows px is reducible, which is contradiction. So no such n exists and the idol generated by px is maximal. The theorem is proved. Third theorem we have is if the polynomial px is irreducible in fx, then px divides the product rx sx implies either px divides rx or px divides sx. We have the proof here. Suppose px divides the product rx sx, This implies the product Rx Sx, it belongs to the ideal generated by Px, which is maximal because the polynomial Px is irreducible in Fx by our previous theorem, so is prime also. Then we have the product Rx Sx belongs to the ideal Px implies either Rx belongs to the ideal Px or Sx belongs to ideal Px. So if Rx belongs to Px implies Px divides Rx, and if Sx belongs to Px, then Px divides Sx. Hence the theorem.